we are going to introduce a new concept called product of inertia. But before that, let me quickly go to take an example of computing moment of inertia in 3D for a 3D object. So, here is the example. So, we have a rectangular prism as shown in this figure, and the question is determine the moment of inertia with respect to the z axis. So, again note that the look at the reference frame. So, when you calculate moment of inertia, first thing is to consider where is the origin, and second thing is to consider that what is the reference frame, that is what is how the reference x coordinate axes are defined. So, the origin, so it is something, so x axis is passing through the middle of the prism. So, x axis is indeed a axis of symmetry for this figure, but the y axis and z axis are not passing through the middle of the prism. So, y axis and z axis are not axis of symmetry. But that has nothing to worry about. So, we cannot readily use the results that we listed in our previous lecture. But now we do not worry about that, because now we know that what is the general formula for calculating moment of inertia about any arbitrary z axis. So, that formula is given by just we need to calculate. Now, we understand what is this moment of inertia. It is the distance of the mass distribution from the z axis. So, we need to take each mass element dm located at some point x, y, z inside the prism, and then the distance from the z axis. So, distance from the z axis is x square plus y square. So, now this mass element dm is, if the density of the material is rho, then and the volume of this element. So, this is a little cubic cell located at with width dx, height dz and breadth dy. So, the volume is dx times dy times dz times density gives us the mass. So, then this is a 3-dimensional integral which goes from rho dx dy dz x square plus y square. Now, we are going to assume, so because it is homogeneous, so I can take the density outside. So, this is going to give as, so I can take the rho outside the integral, and there are two terms. The first term is dx times x square times dy dz, and the second term which is dx times y square dy times dz. Now, this is a rectangular object. So, x, y, z can vary independent of each other. So, we can factorize the integral. So, we get rho times, the first term is x square dx times dy times integration over dz, and the second term is integration over dx, then integration y square dy and dz. Now, all that remains is to put the limits of the integral. So, from the figure x varies from 0 to a. Now, y varies, be careful. So, this is where you need to pay attention to the detail. So, the y varies from minus b by 2 b by 2, and z varies from 0 to c. Then we get our answer. Now, rho we can write as the total mass if is m. So, the mass of the object let us assume to be m, and the volume of a prism is just a times b times c, and then the first term is 1/3 a cube times b times c, and the second term is A times 2 times B square by 4 times C. So, if I simplify it, we get, so this is B cube by 8. So, this becomes 4 and here 1 by 3. So, then if I simplify, so the C gets cancelled from both the term. So, if I simplify, we get I ZZ is M by, so the first term has 1 by 3 and the second term has 1 by 4, 1 by 12. So, we take 1 by 12 out, then the first term will have 4 s square and the second term will have only B square, and this is the answer. So, so far the moment of inertia x x, y y and z z, this measures the spread of the mass distribution about this axis of rotation, if we choose x axis, y axis, z axis as our axis of rotation. Now, often we also want to capture another aspect of the mass distribution, which is that whether this mass distribution are symmetric or asymmetric about our chosen axis. And here we need to introduce the concept which is called product of inertia, which measures if the mass distribution is symmetric or not about our chosen coordinate axis. So, here let us take an example. So, suppose we have a 2D mass distribution, this is a 2D plate and this is some plate, and we want to consider the moment of inertia of this plate, and we have we consider two possible choice of our coordinate system, the blue and the black. Now, we define the product of inertia in the following way. So, we define the so let us say any point, any mass element. So, if this is our origin, then any mass element here of let us say width dx and height dy located at a point x y. Then we define this double integral x y times dm, where dm is this mass element dm, as the component I x y. And similarly, if so, this is a 2D in 2D case, this is the only example, product component that is possible. The in 3D we can define two more analogous quantities. The one is the yz in a 3-dimensional case, yz and integral over yz, which is called the component Iyz. So, the yz component of the moment of inertia. So, note that in the previous case, so now these indices are different, and that is why this is called product of inertia, and similarly Ixz or Izx. Now, there is a crucial difference from the previous case where we were considering the distance. So, these components can be, the sign of this component can be either positive or negative. To contrast, when I define the distance of a mass from the x axis, that was defined to be, so this is always 0, that is non-negative, strictly non-negative, it cannot be negative. Whereas, this combination where we have a mixed coordinates, they can, so each term has only one coordinate in this case, but here each term has a combination of x and y. So, this is a product of inertia. Now, I quickly go through the so for the product of inertia, we can apply the parallel axis theorem, which is sometimes useful. So, here is how it works. So, we consider two reference system, one is x naught y naught. So, G is the center of mass position, and let us say if we take G as the origin and then x naught y naught is kind of a reference coordinate system in which the mass distribution is symmetric. And then we take an arbitrary coordinate system OX at a arbitrary origin location O as our origin, and then the OX and Y are the new coordinate system in which the mass distribution is asymmetric. This is clear because you see that so this x naught axis is sort of passing through the middle of the object. So, it is clear that if there is one mass element dm here, we can also has another mass element in somewhat roughly in the opposite side. So, this is at a position which is symmetric about x axis, and similarly at a position about symmetric about y axis. So, this is the meaning of asymmetric and symmetric mass distribution. Okay, but when you take the other axis, the full object is on one side of the axis. So, this is clear that about OX OY axis the mass distribution is asymmetric. So, then we calculate we write down the definition of the product I x y. So, this is x y times dn. Now, from the figure it is clear that x is given by x naught plus dx. So, dx, so x is the location of this point with respect to the origin O, and x naught is the location of this point with respect to the center of mass. So, and the location of the center of mass in respect to origin O is dx and dy. So, then from the figure the x is equal to x naught plus dx and y is equal to y naught plus dy. Now, if you expand this term, you get this 4 term, and it is easy to show that this 2 term will be 0. Then you end up, so this first term is just by definition the product of inertia with respect to the reference frame which is at the center of mass, in the center of mass frame. So, this is by our notation we define it as x naught y naught. So, I of x naught y naught, and the second term. So, dx dy, when it so you can take dx dy outside integral, then integral over dm will give you the total mass of the object. This is just m times dx dy, and then these 2 term you can easily show from applying the definition of the center of mass that these 2 terms should vanish. So, this is analogous. So, if dy equal to dx, then this will be the distance of the center of mass from this axis. So, this is the analogous of the parallel axis theorem which we so far learnt about the each axis, x axis or y axis. Now, we sort of applied and generalized it to the case of product of inertia. So, now to get us familiarized with this concept, let us work through an example. So, again we take a rectangular prism. So, the prism has mass m and its sides are length a, b and c, and we have taken a coordinate system. So, one corner of the prism is our origin, and then each side of the prism as a x, y, z coordinate system. So, clearly in this particular choice of coordinate system, the mass distribution is on the one side of the coordinate axis. So, this is asymmetric, which means that we expect that the product of inertia to be non-zero by definition. So, the question asks that determine the moments and products of inertia of the prism with respect to the coordinate axis shown, which means we need to calculate the different components I x y, I y z, I z x, as well as which represents the 3 possible products of inertia, and I x x, I y y and I z z, which represents the moment of inertia about the 3 axes are shown. So, let us work it out. So, let us calculate the I x y. So, our definition says, so if I take any mass element located at location x, y, z, so the x coordinate times y coordinate times the mass element, that is an integrate, that will give us the I x y. So, if the density is rho and this is constant. So, I take it out times x y, and this is a rectangular prism. So, x, y, z are independently varying variable. So, I can factorize. So, you have x dx times dy y times dz, and now we put limit. So, x varies from 0 to a, y varies from 0 to b. So, note that now y varies from 0 to b, unlike the previous example, and z varies from 0 to c. So, this will give us rho times half a square times b times c. So, now I plug in, replace density by the total mass. So, this should give us half b square times c. So, this is 1/4 a square b square c. So, upon simplification it becomes 1/4 m a b, and then by symmetry, by switching the indices, you can easily verify that the I y z will be given by 1/4. So, I y z will be 1/4 m b c and I z x will be 1/4 m c a. So, let us work out the I x x component also. So, the I x x will be, so this is the distance. So, this is the distance of this mass element from the x axis. So, this is y square plus z square. So, this will be rho times dx dy dz times y square plus z square. So, this is really a volume integral, and we can factorize x y z coordinate. So, this will be rho times dx times y square dy times dz plus dx times dy times z square dz, and putting the limits. So, 0 to b, 0 to c, x varies from 0 to a, y varies from 0 to b, z varies from 0 to c. So, this becomes, so rho we can write as m by a b c, and then the first term is a times b cube by 3 times c plus second term is a times b times c cube by 3. So, after simplification it becomes 1/3 m b square plus c square. So, 1/3 m b square plus c square, and by switching the kind of a cyclic permutation of the indices, because these integrals are symmetric in x y z. So, we can guess that y will become 1/3 m c square plus a square, and I z will be 1/3 m a square plus b square. So, to summarize, today what we learned is a new concept called products of inertia, and this is a measure about whether a mass distribution, a given mass distribution is symmetric or asymmetric about the choice of our coordinate system. So, if the mass distribution is symmetric, then this quantity is 0. If the mass distribution is not symmetric, then the product of inertia is non-zero. So, in the next lecture we shall consider a new type of problem which is about principal axis and how to find them. Thank you.